Hi there, folks. I'm Jeff Starnes, and I'm going to tell you about a project that I'm working on with Andrew Cohen and Karen Rotello. In the criminal justice system, investigators often ask an eyewitness to attempt to identify the culprit that they saw commit a crime. Eyewitness researchers have investigated the validity of identification evidence for decades. Today, we're going to think about a central question in this endeavor. How valuable is the evidence from an identification attempt? Answering this question is important because there are lots of different ways that you could do an identification, and researchers need to figure out which procedures provide the highest evidentiary value. That is, which procedures best help us figure out which suspects are innocent and which suspects are guilty. There are a number of existing measures of evidentiary value. Different measures highlight different aspects of performance, and that's useful because you can get different perspectives, but it also means that different measures sometimes support different conclusions. So measure 1 suggests that procedure A is better than procedure B, and measure 2 suggests the opposite. It's important to note that all of the existing measures ignore some aspect of identification performance. There are things you can change about performance without changing the measure in any way. And in this sense, they are incomplete measures of evidentiary value. I'm going to introduce a measure of evidentiary value that's rooted in information theory, expected information gain, or EIG. EIG provides a complete measure, that is, it doesn't ignore any aspects of identification performance. So I want to bring you through an example to show how EIG is calculated and to explain the principles that motivate this measure. For my example, I'll use data from the standard simultaneous lineup condition in experiment 3 of Koloff and Wickstead. In this experiment, participants watched a video of a simulated crime, and later they saw a lineup of 6 pictures and decided if any of the pictures showed the culprit that they saw in the video. Witnesses could make a variety of responses. They could indicate that the suspect was the culprit that they saw in the video. That's a suspect identification. They could indicate that one of the other lineup members was the culprit. That's a filler identification. Or they could indicate that none of the lineup members was the culprit. That's a rejection. And all of these responses could be made with high or low confidence. Here, I'm showing you the probability of guilt and innocence conditioned on a specific witness response. The first column shows just identification attempts where the witness made a high confidence suspect identification. 94% of these attempts had a guilty suspect. The suspect shown to the witness was the culprit from the video, and 6% had an innocent suspect. So the high confidence suspect identifications were a strong indication of guilt in this procedure. The second column shows low confidence suspect identifications. Here we have 70% guilty suspects and 30% innocent. So still an indication of guilt, but not as strong as the high confidence. The remaining responses are an indication of innocence. For example, high confidence filler identifications came from 67% innocent suspects and 33% guilty suspects. This sort of analysis is known as the Bayesian approach to defining evidentiary value. This approach has supported important discoveries, but one limitation is you have to work with one response at a time. So we can note that high confidence suspect identifications support guilt with 94% certainty, or high confidence rejections support innocence with 71% certainty. But there's no way to put it all together and define evidentiary value across all of these responses. There's another existing approach that does combine across all the response categories, and it's known as the expected utility approach. Expected utility meets this goal by assigning a value to each possible outcome of the identification attempt and calculating the average value achieved across all identification attempts in the dataset. One limitation of the expected utility approach is that identification responses are linked directly to consequences, and then those consequences must be assigned a set of values with no hard and fast rules to determine what those values should be. Expected information gain acknowledges that there are several steps that intervene between an identification response and a consequence in the criminal justice system. As a first step, agents of the criminal justice system need to use identification responses to inform judgments about whether a particular suspect is guilty or innocent, and how certain they can be about that given the evidence available. As a second step, agents of the criminal justice system need to make a variety of decisions that are informed by those judgments of guilt or innocence. And only then do we get consequences. A guilty person goes free because a detective decided not to investigate him. An innocent person goes to jail because a jury decided to convict him. There are a huge range of possible outcomes that we probably can't capture by just a few numbers. But luckily, we don't have to. Eyewitness memory researchers are trying to find the procedures that produce the highest evidentiary value. We're looking at the first step, and if we can figure that out, then we're setting people up to make the best decisions that they can and to achieve the best consequences that they can. So we want to define the intrinsic value of evidence. Luckily, Claude Shannon already worked that out for us in the seminal paper of information theory. Evidence helps you make better judgments, and judgment success can be quantified as a function of the probability assigned to the true state of affairs. The critical measure that Shannon proposed is called surprisal. It's the logarithm of the inverse of the probability assigned to the true state of affairs in a judgment. It indicates the level of error associated with a probabilistic judgment. For example, say we have a suspect who is in fact guilty. If someone judges a high probability that they are guilty, that leads to a low surprisal, indicating a low degree of judgment error. In other words, learning that the suspect is truly guilty wouldn't be that big of a surprise because you already judged that that was likely to be the case. If you assign a low probability of guilt, then surprisal is high, indicating a high degree of judgment error. You think the suspect is innocent, and the suspect is in fact guilty. So learning the truth would surprise you to a great degree. This is measured in bits, where one bit of information doubles the probability that you assign to the true state of affairs. One great thing about this measure is that it provides a way to figure out if you've set yourself up to make good decisions. High surprisal judgments motivate bad decisions, and vice versa. For example, say we have a suspect who is in fact innocent. If someone is convinced that that suspect is guilty, that's a high surprisal judgment, a high error judgment, and it could lead to some very bad decisions, like convicting an innocent person. So we're looking for procedures that give us the sort of evidence that convinces us that the guilty suspects are guilty and the innocent suspects are innocent. So let's try this out. The police have a suspect to a crime. Is that suspect guilty or innocent? Well, you don't know. It's really hard to judge. There's not a lot of information to go by. Our data set is a great example of that. Half of the identification attempts had a guilty suspect and half had an innocent suspect. So without any further information, the best you can do is judge that there's a 50% chance that the suspect is innocent, 50% chance that they are guilty. Now, imagine you learn that a witness identified the suspect with high confidence. Let's reassess whether that suspect is guilty or innocent. For our data set, you should judge that the suspect is guilty and be 94% certain that you are right. So what is the value of learning this witness response? That depends on how much it helps you improve judgments of guilt or innocence. For example, consider a guilty suspect who receives a high-confidence suspect identification. Before learning the witness response, surprisal is 1, because you judge a 50% chance that this guilty suspect is guilty. After learning the witness response, surprisal decreases dramatically because you judge a much higher probability of guilt, about 94%. And note that the values in the table are rounded, and I didn't round for the calculations. So we can look at how much your judgments have improved, and they've improved by 0.92 bits. So you've obtained just under 1 bit of information by learning this witness response. 1 bit is something that doubles the probability you assign to the truth. So that'd be like going from a 50% to a 100% judge probability of guilt. We fell just short of that. What if we get a high confidence suspect identification for an innocent suspect? In this case, the surprisal before the witness response is still 1. You judge a 50% chance that this innocent suspect is innocent. The surprisal after the witness response increases dramatically. So the witness response convinces us that the suspect is guilty, and we assign a low probability of innocence, which is the true state of affairs. Surprisal goes up to 4.17 for a difference of negative 3.17. We've lost just over 3 bits of information by observing this witness response. That means that the probability we assigned to the truth got cut in half, and then cut in half again, and then cut in half again. That would be losing 3 bits of information, and we're a little bit below that even. So we're in a worse position to make good decisions after seeing the witness response than we were before seeing the witness response. We can fill in the remaining cells of all the other possible identification outcomes. All of these values are based on the change in judgment success produced by learning the witness response. We have positive values when the witness response helps convince us of what's actually true, when we get a response that indicates guilt for a guilty suspect, or a response that indicates innocence for an innocent suspect. And the values are negative when we get a witness response that misleads us. Now we get to the best part of using Shannon surprisal as a measure. This measure can be validly averaged to characterize average information. So all we have to do is take the weighted average of all these outcome values, weight it by the probability of achieving that outcome, and we've characterized the evidentiary value of the procedure as a whole. So for example, a high confidence suspect identification for a guilty suspect is worth 0.92 bits of information, and that happens 17% of the time in this procedure. So we multiply those two to get the weighted contribution of that cell. A high confidence suspect identification for an innocent suspect is worth negative 3.17 bits of information. That happens 1% of the time. We multiply those two to get the weighted contribution of that cell. So we do this for all of the cells, add it up, we have our weighted average, 0.18. That means that conducting an identification attempt with this procedure produced 0.18 bits of information on average. Maybe you don't really think in terms of bits. Well, you know what? You should start. I've been having a lot of fun with it, but for now, you can note that this is the same amount of information as going from 50% to 74% certainty in guilt or innocence. So definitely not perfect information, but the procedure tends to give you a somewhat useful indication of whether a suspect is guilty or innocent. So now you may be thinking, wow, that was pretty dry, even for a MathPsych talk. So in the last minute here, let me assure you that this is pretty cool. There's lots of things that we can do with the EIG measure that couldn't be achieved with existing measures. First, it allows us to compare the evidentiary value of procedures, all things considered. It gives us a complete measure of evidentiary value. So that's certainly important for policymakers who should be factoring in all the relevant factors. It can be used to compare procedures even if they have different response options. It can be used to quantify the value of continuous predictors of witness accuracy, like response time, and all kinds of other great stuff. Okay, so the important take-home message is that expected information gain provides a complete measure of the intrinsic evidentiary value of an identification procedure. Thank you for listening.